Good morning, class. So we have 3 videos for this week talking about forces at angles. The first one's just going to be talking about like how does one angle, let's actually move closer, there we go. How does moving something at an angle actually change our, how we're going to find our actual net force and our acceleration. So that'll be video 1. Video 2 will actually be finding that acceleration. And then video 3 will be me, if you're given the force applied and everything, how would you possibly find mu? So that'll be our 3 videos for this week. If you were in the lab, this will sound very similar as I did kind of 2 activities that cover this with you. If not, then hopefully these videos help as well. You can always ask me questions. So let's kind of go through this. So I have a little picture here as well. So hopefully you're able to see that I'll use this example, this little block on a string, which is what we used in the lab. So let's get at it. In any question, in this one we're going to try and find basically like what's the acceleration. So we're going to kind of go, I'll put it down here, acceleration, question mark. Okay? So in the end, what is our acceleration of this problem? We have a 20 kilogram mass that is being pulled at an angle of 45 degrees. So imagine kind of like pulling someone on a sled. The string makes a 45-degree angle. Okay, again, remembering straight across. Straight across is 0, straight up is 90, so 45 degrees somewhere in that middle. Okay. So there's our 45-degree angle, and they're pulling at 250 newtons, which is pretty strong. So let's try and figure out like what do we end up needing here to figure out our net force. Well, you're gonna have to figure out what's the force moving in this direction, and then also the force of friction. So eventually we'll have to find the force of friction. Now, the first thing that we're going to start off with here is, can I just use this 250 to say how much force is being moved in this direction? Well, first we kind of have to think of when you're pulling on a sled sideways, even if you're pulling at an angle, so even if you're pulling a sled at an angle, does the sled move in like this angle? Does it move in like this kind of diagonal? And the answer is no, the sled doesn't. Like you pull at that angle, but the sled moves straight across the ground. It moves again on the ground. It doesn't magically start floating up at that angle. So we kind of need to know what like just that force is when it's moving just along the ground. And to do that, we kind of need to add a new part to our a new like formula and a new section to our actual forces. So we've had these 2 formulas the whole time. F equals m times a, and that's always like net force equals mass times acceleration. We have force friction equals coefficient of friction times force normal. Now we're going to have to like be able to break this into 2 pieces, okay? And we kind of did this in vectors a little earlier on. We're going to have what's called an fx, which is this, as in like the force in the x direction. And we're going to have an fy, which is like this, the force that you're pulling in the y direction, okay? If we kind of figure out a little trick over here, if I kind of go SOHCAHTOA, so I have SOHCAHTOA, and I know they never go away. SOHCAHTOA will never go away. They just keep coming back. Trig is important for us. Whether you're in engineering, whether you're in architecture or physics, it always comes back. So if we're looking for this, we have the hypotenuse, we have the 250 here, we have the angle, we need the adjacent, which is the one touching here. So we're going to use cos to find that. So for x, and this will be in your notes, like our notes / your formula sheet that I put up there. Cos of the angle times force applied. This is the opposite side, so we have sine. So for Fy, it'll be sine theta times force applied. So let's kind of do this and actually find what force x would be and what force y would be. Okay? And I'm going to put that information over here. So we have mass of 20, force of gravity just times by 9.8. I get 196. Here's where we're going to try and find force x and force y. So if I go cos of 45, which gives you like 0.707 or something like that, and then times by 250, I get an answer of 176.7. If I go for Fy, finding the y, how much force am I kind of pulling up? Because again, when you're pulling this way, you're pulling both kind of in the x direction and the y direction. So the up and down direction as well. If you go sine of 45 times force applied, you get the same answer, 176.7. You're like, well, That doesn't make sense. I use cos for one, I use sine for other. Why do I get the same answer? And the reason is because you're at 45 degrees. If you kind of imagine this, put my marker down. This, if you pull straight sideways, that's all in the x direction. Okay, so you're pulling right in the x direction. If I pull straight up, I'm pulling all in the y direction. So if I'm at 45 degrees, which is in the middle, I'm going to get exactly the same x and y numbers. Now in other questions, let's say you pull at 20 degrees, you're going to have a lot more x than you will y. And if I pull it like 70 degrees, you're going to have a lot more y than you will x. And that kind of makes sense. You can kind of see it there. So more x, more y. If I'm at 45 degrees, it's about the same. Okay, so now that we have the force x and force y, this x is really the important, like one of the big important parts. Force x equals 176.7. Because that's going to tell us how much force is being pulled this way. Like, yes, you're pulling with 250, but it's not in the direction that the kid in the sled is actually moving. That's the force. So that's kind of like part of our net force. We have this going this way. Now we need to find force of friction. How do we find force of friction? Well, we need the mu, the coefficient of friction, times force normal. We have mu. It's going to be given to you, so that's good. Now we just need to find our force normal. Well, how do we find force normal? Again, in a nice world, it would always be the same as force of gravity, which is just 20 times like 9.8, which is 196. So in a nice world, that would be exactly the same. But again, let's kind of go over what force normal is again. Force normal is like the table or the ground holding something up. So for an example, this block right here is on the table. Okay, there's a force of gravity on the block, and the table's holding up, which is great. Okay, if I were to sit on this table, again, the table would probably hold me up. There's a force of gravity on me, and it's pushing down on the table, and then the table holds me up, so it has to actually hold up. So right now, there's a force of gravity on the block, and the table is doing the exact same. It's pushing up the same. Well, if I do this, what is the force normal for the table? How much work is the table doing now? Well, nothing. I'm doing all the work. The table's not touching the block. So if this force normal is 0, because the table is doing no job, and now the force normal is exactly the same as force of gravity, what happens if I do kind of this? I'm pulling it, I'll do the turn it this way. What happens if I do this? I'm pulling it at an angle. Well, is the force of gravity and force normal going to be the same? Is the table still doing all the work? And the answer is no, I'm doing some of the work. So the table doesn't have to do all of the work anymore. I kind of use this analogy, which is a weird one, but that's okay, it works. So if you're lying on the ground and someone lays on top of you, you feel all of their force. If someone starts trying to pull them off of you, well, now you don't feel as much force because they're helping you. They're trying to get that person off of you. So you're not going to feel all of that force. Okay, and so we can kind of work that into our numbers here as well. For force normal, we still have the force of gravity pushing down. The block is still having a force down, but we're going to minus it from our force y, the one in the y direction, the one going up. And that's because you're helping it pull up. You're not going to let the ground do all the work. You're helping it. And so that's how we're going to find force normal here. And so when I go 196 minus 176.7, you're going to get an answer of 19.3. 19.3, and that's force normal. Okay? The last thing that we have to kind of find here is our force of friction. All right, so force of friction here equals, again, it equals mu, so 0.25 times force normal, 19.3. So that's going to be the answer of 4.8. 4.8. Oh, yeah, so I put that 4.8 right here. 4.8. So these are all the forces that are going to go into this question. I know there's kind of a lot there. If you look down, there's a couple here and there's some here. There's a kind of a lot of forces to go through one question, but now we've got the full picture. This will be the end of the first video because we're getting close to that 10-minute mark. In the second video, I'm going to start back up right here, and I'm going to talk about what happens if Fx is bigger than force friction. What happens if force friction is bigger, and kind of the details of actually how to find your acceleration, okay? In this video, we found all the forces. These are all the forces you're being able to find. In the next video, I'm going to show you how to kind of think about these and how to find your next steps. Thanks, class.